Okay, so let's begin with what we're going to call orbitals. And this is the most common model. It's often referred to as the Rutherford model. Rutherford was one of the first scientists to deduce the location of the nucleus. And this model persisted for a while, but we've since come to learn that it is incorrect. And we're going to be using a model devised by Niels Bohr. So let's jump in. According to the Bohr model, electrons don't orbit the nucleus at infinitely variable distances where they can be found anywhere in this area. As a matter of fact, they exist in particular areas. And it's not that we know exactly where an electron is. We just happen to know that you could find an electron in this area, you could find an electron in this area, and you could find an electron in this area. They're called orbitals. They're more like rooms on a floor, but we'll get into that as we go. So we said that energy levels are like the floors in a building. And on each floor, you have rooms. These are what we're going to call orbitals. And remember that each can hold a total of 2 electrons. Well, this is what orbitals look like. And they're a weird shape. I mean, we've got some s orbitals that are kind of shaped like a ball, and then we've got some p orbitals that are kind of shaped like a peanut, and then we've got d orbitals that are kind of shaped like this kind of X shape, and so on and so forth. Let's remember that no matter how weird these rooms get, they can each only hold 2 electrons. As long as we keep that in mind, these can get as weird as they want, but they don't have to bother us because they are just different shaped rooms. Okay? Keep that in mind. So let's start with our energy levels, and they are like floors in a building. The higher up you go, the more energy you have. In that, the higher up you go, the more work it takes to get there. And that's the same with electrons. The higher up you go, the more work it takes to remove that electron from the pole of the nucleus, which, let's recall, is positively charged. Electrons being negatively charged, there's an electrostatic attraction. So the higher up you go, the more energy you have. Which is very similar to a building. But unlike a building, the higher up you go, the more room you have. So the lower energy levels aren't as big as the larger ones, as the energy levels higher up. So let's start on the very bottom energy level. Remember that principal quantum number is another way of saying what floor are we on? We're going to represent it with lowercase n. And it's going to be a whole number that represents what floor of the building we're on. So energy level 1, and we're on the first floor. And let's remember that the higher we go up, the more room we have. So on the first floor of a building, there isn't much room. There's only one type of orbital available. And how do we know there's only one type of orbital available? Let's do a quick calculation here. When n equals 1, L can be any value that is equal to 0 up to n minus 1. Well, when n is equal to 1, there's only one possible value for L, and that's 0. And that tells us how many orbital shapes are available. And that means this is only 1. All right, let's take a look at what it looks like. So when we're at energy level 1, n equals 1, and L has has only one possible value, 0. That's this guy. So at energy level 1, there's only one type of orbital available, and it is shaped like a sphere. So we're going to call it an s orbital because that's what it looks like. And there's only one type of orbital available. Now we're going to go up to energy level 2, n equals 2. Let's remember that when n equals 2, the possible values for L can be anywhere from 0 to n minus 1. That means our values for L can be 0 or 1. And that means that at the second energy level, there's an s orbital available. If you look, you can see it right here. We've got more energy, and so the orbital is bigger, and that means that our sphere takes up more space. You can see it here. The s orbital from energy level 1, what we're going to call 1s, is right here, and it's pretty small. But the energy level 2 s orbital is a little bit bigger. You can see how it takes up more space. It doesn't mean it can hold more, it's just a bigger room. It's higher up in the building. However, when we go up to energy level 2, that means we have a new type of orbital available, what is indicated by the angular momentum quantum number 1. What does that look like? Let's go check it out. So a second energy level, meaning higher energy, means we've got more room. And let's recap. We know that when energy level n equals 2, L can be 0 or 1. And that means that m sub L can have multiple values. M sub L can be any value that is equal to from negative L up to positive L. When L is equal to 0, there's only one possible value for M sub L, and that's also 0. But when L is equal to 1, like it is at energy level 2, we've got a different shape orbital. That can have 3 different values of M sub L. And each of these is going to be a different orientation. That means that this orbital, indicated by L equals 1, has to be kind of weird. And it is. It has to be a funny shape because remember that these are holding electrons that normally want to repel. So they have to stay out of each other's way so the electrons don't bang into each other. And that means that this new shape of orbital is going to look a little funny. This new type of orbital looks a little weird. In fact, it looks like a peanut. We're going to call it the p orbital, and it is only available at energy level n equals 2 and beyond. So we don't expect to see this any earlier than that. And because it has this weird shape, this peanut shape, it means that it can flip around in different orientations to stay out of its way. And let's remember that m sub L for L equals 1 is negative 1, 0, or plus 1. That means that there are 3 possible orientations. Let's take a look. So here are our 3 orientations for p orbitals. Remember that when energy level n equals 2, L equals 0 or 1, and there's only one possible orbital for the L equals 0. That's our S. But there are 3 possible values for m sub L when L is 1, and these are going to be our P's. Here is the first one, and it's kind of arranged on this axis, so we're going to call it the PZ, stands vertically. I don't know why they didn't call that the y-axis, but that's okay. This one's arranged along the x-axis, so we'll call that the PX, and this one's arranged around the y-axis, we'll call it the PY. If you superimpose this one over this one over this one, you'll see that they don't interfere with each other, so they can each hold 2 electrons without getting in each other's way. Okay, we're going up to the 3rd floor. So here we are on the 3rd floor, and now n equals 3. that means that L can have values of 0, 1, or 2. And that means that there is now a new shape. Well, what are our original shapes? We've got our s orbitals. That's the 0. And look how much bigger it is right here than the 1s or the 2s, because we've got even more energy. And that means our orbitals are bigger. They still only hold 2 electrons, but they're bigger, so they stay out of the way of the others. And that's our s. And we also have our p's, which are going to be bigger. Let's take a look. And we also will have a new shape that we haven't seen yet. So let's take a look at what our p's look like. Okay, here are the 2p orbitals right here. And notice that they are lying along these 3 different axes like we've seen before. But at the third energy level, we have p orbitals, but they're bigger. And if you look in this diagram here, you'll see that the 2p orbitals are in there, right there, and you can kind of see them in there. But the p orbitals are way bigger. I mean, the 2p's are, there's one in there, and you can kind of see this one in here. But the 3p's are bigger. And let's also remember that we have this new shape that we haven't seen yet, only at n equals 3 and beyond. So what's this one going to look like? Let's take a look. Here is the new type of orbital we're only going to see at energy level 3. When n equals 3, there are 3 possible values for L, and of these values, for L, you can have 1 value for m sub L, 3 possible values for m sub L equals 1, and now you can have 5 possible values for m sub L when L equals 2. And each of these are a new orientation of this new type of orbital that we're going to call the d orbital, because it's kind of shaped like a double peanut, I guess, if you squint. So let's take a look at what these 5 possible orientations are. And so this is our double peanut arranged in our 5 possible orientations. And let's remember that each of these can hold 2 electrons. Even though they're really weird looking, they're still only holding 2 electrons. If you superimpose these images over each other, you'll see that they stay out of each other's way pretty well. I mean, this guy's kind of goofy looking, but it does the job. And so that brings us to our 4th and final energy level. So let's do a quick recap. At energy level 1, n equals 1. There's only 1 possible value for L, and that means only 1 possible value for m sub L. Meaning, at energy level 1, there's only 1 type of orbital, the s, and there's only 1 type of orientation, which is all you can have for a sphere. At energy level 2, n equals 2, L can be 0 or 1, and that means that there is 1 value for 0 and 3 for 1, which means 4 possible types of orbital. The s is 1 type, and the p is another type, and there are 3 orientations. At energy level 3, where n equals 3, there are 3 possible values for L, and for m sub L for each of these, there is 1 value for 0, 3 values for 1, and 5 values for 2, which correspond to the 1 way you can orient an S, the 3 ways you can orient a P, and the 5 ways you can orient a D. So here we are on the 4th floor. Last one. Here on the 4th floor, we've got more energy, and that means that our s orbitals, which are the spherical ones, are bigger. And our p orbitals are bigger. There's the 2p in there, there's the 3p there, and here's our 4p. And we've got our d's at the 4th energy level. There they are, and just like in the 3rd energy level, there are 5 of them. They're just bigger. And so here we are at the Last type of orbital. We're at energy level 4. L can have values of 0, 1, 2, and here is our new orbital, 3. And how many orbitals can, different arrangements? Well, for L equals 0, that means there's only one possible value, also 0. For 1, we can have -1, 0, or +1. There's our 3 p orbitals. Here is energy level 2. You can have, this is L being 2, you can have -2, -1, 0, +1, or +2, meaning 5. Here is our new orbital. This can have values of -3, -2, -1, 0, +1, +2, or +3 for a total of 7 possible orientations. Ladies and gentlemen, are you ready? Here is our new orbital, the F. And remember that there are 7 ways to orient this one. And just like all the others, each of these, no matter how weird they look, and some of them look pretty weird, can only hold 2 electrons. We only see F orbitals at n equals 4 and beyond. And for our purposes in this class, F is the last type of orbital. So we're not worrying about anything weirder than this, even though there are. We're not going to worry about them. Okay? So, energy level n being 1 has only the single 1s orbital, and it can hold a total of 2 electrons. Energy level 2 has 2 s orbitals. It has 1 of them, and it has 2 p orbitals, 3 of them, and they can each hold 2 for a total of 8. Energy level 3 has 1 3s orbital, which can hold 2 3p orbitals, which can hold a total of 6 between them, for a total of 8, and 5 ds for a total of 10. That means they can hold a total of 18 electrons. If you count the rows of the periodic table, the columns, you'll see that there are 18. And how about our Fs? When energy level n equals 4, values of L can be 0, 1, 2, or 3. And here is how our values of M sub L stack up. For 0, there can be only 1. For 1, -1, 0, and +1. For 2, -2, -1, 0, +1, and +2. And for 3, -3, -2, -1, 0, +1, +2, +3. If you count up each of these, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, you'll see that they can hold a total of 32 electrons at the 4th energy level. You're going to say, well, Mr. O, the periodic table only has 18 columns. I will show you what it looks like and how we get 32. Okay? All right, take this for a spin, please.